Hi guys, Mr. Gillen here, and during this video we are going to discuss trigonometric graphs, or trig graphs for short. So first thing we're going to do is we are going to look at what a sine graph, a cosine graph and a tan graph look like, just the standard ones, and from there we are then going to look at how to read them and then how to eventually sketch them as well. So this is a sine graph, as you can see. It's got roots at 0 degrees, 180 degrees and 360 degrees. So if you look at the axis that we've got just now, it's a bit different from your x and y sometimes, but our roots are 0, so where it crosses the x-axis, 180 and 360. It's got a maximum value at x equals 90 degrees. So where x is 90 degrees, we can see it is where the graph itself reaches its highest point. You might recognise that as a turning point. It's got its minimum value at x equals 270 down here. So we can see that that appears at -1. So its highest value is 1, lowest value -1. What we call the domain, it takes place. So you can see it starts at 0, goes all the way up. When we get to 360 degrees, that's where if we were to continue this graph on, it would start to repeat itself. So the domain is 0 to 360. As we say, a maximum value of 1 and a minimum value of -1. And the way that we would write this is we would just say y equals sine x. If we have a look at the cosine graph, it looks similar but at the same time different. We get roots at 90 degrees and 270 degrees, so there are our roots there. And different to the sine graph, the maximum value in the cosine graph happens when x equals 0 and when x equals 360. So there's our max value. The minimum value happens at 180. Again, the domain is 0 to 360 degrees. So when it gets to 360 degrees, like the sine graph, it would start to repeat itself. And the way we would write this one is y equals cos x. This is the tan graph, which looks a lot different from the sine and the cosine graph. For the tan graph, it has roots at 0 and it has roots at 180 degrees. The domain for the tan graph is slightly different from the sine and the cosine graph. You'll notice that when it gets to 180 degrees on the x-axis, the graph starts to repeat itself. And we would write that as y equals tan x. Now we don't have a minimum and a maximum value for the tan graph because as it trends up the way, it goes on forever. So let's have a look then at what we can do with the graphs and how maybe sticking certain numbers can affect the graph. So let's draw y equals sine x. So we can see, like we had earlier on, we've got our roots at 180, 0 and 360. Our maximum value is 1 and our minimum value is -1. What happens if we start adding numbers? If we were to put a 2 in front of the sine x, what we would find is the graph starts to get taller. Okay, so that 2 has increased the maximum value to go up to 2, and it has made the minimum value go to -2. If we were to stick a 3 in front of it, then as you can see, the maximum value stretches to 3 and the minimum value stretches to -3. If there is a number less than 0, then what we'll see is the graph starts to become compressed and the maximum value becomes 0.5 and the minimum value becomes -0.5. So what effect does the number at the front have on the graphs? Well, it stretches it or it compresses it in the y direction. If we were to put a negative in front of it, so we've got y equals negative sine x, then what happens is we get a mirror image of y equals sine x, where the maximum occurs at x equals 270 degrees and the minimum occurs at x equals 90 degrees. And if we flip that over, we can see it as an exact mirror image of the graph. Let's have a look at the cosine graph. If we have y equals cos x, then we can see there it has its minimum value at 180 degrees for x equals 180 degrees. It's got its maximum values at x equals 0 and x equals 360. And it's got a maximum value of 1 and a minimum value of -1. If we do the same thing again and we put 2 in front of the cos x, the same thing happens. We are able to stretch the graph in the y direction. If we put a 3, we get the same thing. It stretches again. And just like the sine graph, if we put in the 0.5, then it compresses it. So again, the effect that it has is it's either stretching the graph in the y direction or it is compressing the graph in the y direction. And also, the same as the sine graph, if we have a negative in front of the cos, then it produces that mirror image of its positive equivalent. So, what we can say then is, if the repeating pattern has a minimum and maximum value, then half of the difference between these values is something that we call the amplitude. Okay? And to give you an idea, this is what we're looking at. So our amplitude is half the difference of the maximum all the way down to the minimum. Find the amplitude from a graph, find the difference between the maximum and minimum values, and then half it. Next thing we want to look at is we want to look at the repeating nature of the graphs. And what we say is when a pattern repeats itself over and over, it's said to be periodic. Our sine graph, our sine function, has a period of 360, which means that when we get to x equals 360, the graph starts to repeat itself. So let's have a look at how that measures up visually. Again, let's draw in y equals sine x. We've said already that when we get to x equals 360, it would start to repeat itself again. So what happens this time? Instead of putting a number in front of the sine, we put a number in front of the x. What we find that happens is the graph repeats itself earlier on. Or what we can say is that the graph, as you can see here, repeats itself twice within 360 degrees. If we put a 4 in front of the x, then as we can see, the graph will repeat itself 4 times within that domain of 0 to 360. And we can see that at 90 degrees for y equals sine 4x is where it starts to repeat itself, which makes sense because 360 divided by 4 is 90. What if we put a number that's less than 1 in front of the x? Well, what we find happens with that is it takes longer for the graph to repeat itself. So it's almost like stretching the graph out. So what effect does a number in front of x have on the graphs? Well, it affects how many times a graph will repeat itself in 360 degrees. Let's have a look at the cosine graph. So we've got y equals cos x drawn in there. If we add a 2 in front of the x, then what we find, very much in the same way as the sine graph, the cosine graph repeats itself twice as well. If we add a 3, we find the same thing happening again. It now repeats itself 3 times in the graph. And what we would notice is for y equals cos 3x, it starts to repeat itself at 120 degrees, which again makes sense because 360 divided by 3 is equal to 120. So what we can see then is, instead of writing just y equals sine x and y equals cos x, we can say y equals a sine bx and y equals a cos bx, where a and b are numbers. The a, it affects how much the graph is stretched in the y direction or compressed. So if a is greater than 1, it stretches the graph in the y direction. If a is less than 1, then it compresses the graph in the y direction. And as we saw earlier, when a is negative, it flips the graph in the x direction. So it gives us a mirror image. We don't have an a in front of the tan graph because it has no maximum. We can, however, put the b in with the tan graph, with the tan equation. And the b is going to tell us how many times it repeats itself in 360 degrees. So, what we can say is, in general, for y equals a sine bx and y equals a cos bx, the amplitude is a and the period is 360 divided by whatever number b is. Like we saw with the previous graph, where when it was y equals cos 3x, the period was 120, because 360 divided by 3 is 120. Y equals and bx, the amplitude can't be measured, and the period is 180 divided by b. Remember the original tan graph, it started to repeat itself at 180, so be mindful of that. So let's have a look at some different graphs and some different ways that we would have to actually read a graph. We have got the first example where we can see the graph itself is between 0 and 360. So we've got 0 is where it starts and it's there. We can see that at 180 degrees, the graph has started to repeat itself. So the period is 180 degrees, which means that in 360 degrees, it's actually going to repeat itself twice. We can also see that the maximum is at 0.5 and the minimum is at negative 0.5. So for that red line, we can say that its equation is y equals 0.5 sine 2x, because we've got a maximum of 0.5, minimum of 0.5. So the amplitude is 0.5 and it's repeating itself twice. If we have a look at another one, this time the graph is repeating itself 1, 2, 3, 4 times, and the amplitude for this graph is going to be 2 because the maximum value is 2. So we can say that this one is going to be y equals 2 sine 4x. Let's have a think about this one. The graph isn't fully repeating itself in this 360 degrees. You're only getting half of it. What we should also notice is that usually a sine graph would start in a positive direction first, and it is going down to negative 3. So what we're going to have to say here is our amplitude is 3. However, it's the mirror image, so it's going to be negative 3 sine. It's only repeating itself half of the time, halfway in 360, so it's going to be 0.5x. That one's a very tricky one. It's very interesting how, even though all three of these lines are sine graphs, they look so different. And it's all to do with the numbers that have been placed in and around them. Let's have a look at some examples with a cosine graph. This time, our maximum value, or our amplitude, is 1.5. I know it's a cos graph, and it is repeating itself once, twice in 360 degrees. So my equation for it is going to be y equals 1.5 cos 2x. This time, instantly what sticks out for me is the graph is starting from a negative number, which means that the graph is going to be negative. The amplitude is -2 or 2. So I know I'm going to start with -2 cos, and again, the graph begins to repeat itself at 180 degrees, which means that it's got 2x. For our purple one, it's going to be positive because the graph is starting and then going down. I've got an amplitude of 0.5, so I'm going to have 0.5 cos. And now I want to see how many times it repeats itself. So there's 1, 2, 3, 4 times. So let's look at a more complex version of those examples. We are given a graph here and we're asked to find the period and the amplitude of the function shown in the diagram. So first thing we want to look at is how many times does the graph repeat itself? Well, there it's repeated once, twice, 3 times, 4 times, 5 times. So it repeats itself 6 times in 360 degrees. So what we can do then is to find the period, we can do 360 divided by 6, which is 60 degrees. So our period is 60 degrees. Know that the amplitude is going to be 3, because if you're not able to just visually see where the middle of the graph is and then the amplitude up, what we can also do is take our maximum, which is 1, and our minimum, which is -5, and we can find the difference. So we can do 1 take away -5, which is 6, and then our amplitude is going to be 6 divided by 2, which is 3. if we have y equals a sine bx, and then we add on a c, we add on a constant, this is the last part we're going to look at, we're going to see what that does to the graph itself. We know that a is the amplitude, we know that b is how many times it repeats itself, c is how many places the graph has been moved up or down. So we saw that in the previous example. The graph had been moved up and down the y-axis, and that's where this c comes in, this number c comes in. And that becomes very important for the last part of this, for sketching the graphs. If we are looking at y equals sine a sine bx plus c, or y equals a cos bx plus c, then the key points that we need are the maximum, the minimum, and the roots, where the graph is going to cut the x-axis. We're going to use our knowledge of b to know how many cycles of the graph is going to fit into 360 degrees, or how far left or right it has moved. We will come back to that last part in a future video. A is going to be half the distance between the maximum and the minimum. Remember, A is the amplitude. And C, this new idea, is how many places the graph is going to be moved up or moved down. So let's look at one example. We want to sketch the graph of y equals 3 sine 2x plus 1. Our amplitude, we need to know our amplitude for drawing a graph, is going to be 3, because we've got 3 here, so that's going to be our amplitude. Period is going to be 360 divided by 2, and we know that that 2 is coming from here. So there's going to be 2 cycles of the graph, and the first one is going to end at 180. The second one will be between 180 and 360. We know that the graph is going to move up by 1 place because we've got this plus 1 at the end of the equation. So we know that the sine graph is going to have roots at 0, 180 and 360 degrees. It's going to have a maximum of 1 and minimum of -1. That's for a standard sine graph. And we can divide the roots and the turning point by 2 to get new values. Our graph for y equals 3 sine 2x plus 1, we know that it's going to have an amplitude of 3, so it's going to go up 3 and down 3. We've added 1, so for our maximum and minimum, it's going to be 4 and -2, and we'll see more of that when we draw the graph. So we're going to draw the graph y equals 3 sine 2x plus 1. If I was to just draw the simple y equals sine x, if it was going to go up to 1, down to -1, and only repeat once, it would look like that. Okay, that's y equals sine x. Now, we know that our new graph is going to have an amplitude of 3 and negative 3. And we also know it's going to repeat itself twice in 360 degrees. So if it didn't have that plus 1, it would look like that. But we know it's going to be shifted. It's going to be shifted up the way. We're adding 1 onto the values. So if we get rid of y equals sine x, if we shift our graph up, that's what it's going to look like. Notice that we have added 1, added 1, added 1, and we've added 1. So everything has been shifted up the way by 1. Even the origin of the graph where it started has been shifted up by 1. Okay, thanks very much for watching. If you've got any questions, as always, please don't hesitate to get in contact with us. This is Mr. Gillen signing off. Speak to you all soon.